Good day. My name is Conrad Pantua, and I'm based from the United Kingdom, and I'm a PhD student at the University of Nottingham in Nottingham City in the United Kingdom. So today I'm gonna present about my topic, which is energy generation and disaster resiliency modeling framework for extreme weather resilient communities. I'm also associated with the Mechanical Engineering Department of De La Salle University, Manila, the Philippines. So my nationality is Filipino, but I'm studying here in the UK right now. A brief background is that the Philippines is the most populated country in the world with around 100 million people and ranks as the third most risk-prone country in terms of natural disasters in the world, which is visited by an average of 19 to 20 tropical cyclones every year. So we're visited by a lot of typhoons, about 20 in a year, and this will our historical occurrence of typhoon disaster in the Philippines for the past 50 years. This one is the number of deaths. As you can see, in 2013, the deaths spike up to about 7,000, and this is due to the fact that Typhoon Haiyan hit our country. Typhoon Haiyan at that time was the strongest typhoon who ever made landfall. It made landfall at November 8, 2013, and the highest speeds it has sustained wind speeds of around 315 kilometers per hour and gusts reaching about 380 kilometers per hour. And it was the strongest storm recorded at landfall at that time. So damage-wise, we're about 6,300 people died, 28,000 people injured, and about 16 million people affected. And in terms of infrastructure damage, around 1.1 million homes were destroyed or damaged. And economic impact is about 12.9 billion US dollars. These are the pictures from the city of Tacloban, which reported about 90% infrastructure destruction. So this is the path of the typhoon. This is coming from the Pacific Ocean. So it passed through the Leyte Gulf and made about several landfalls in Tacloban, Palo, Tanawan, Tolosa, and Guian. So it made first landfall in Guian and went westward towards the Leyte province. Tacloban is the most populous city in that province, and that's why it has a lot of casualties and damage. So as you can see, the damage that was incurred in the path of the typhoon are mostly the roofs were gone. Just these. So sample is this one. So the roof, because of the strength of the winds, the damage occurred in the roof mostly, and this is caused by the water. Most of the people who died in the storm drowned because of the storm surge, but most of the infrastructure damage was caused by the wind, strong winds. At the same time, if you have renewable energy systems mounted on the roof, it will be most likely be destroyed as well, just in this case. So in the Philippines, solar PV panels installed in roofs. Mostly they are installed in the upper middle income class or upper classes. And around, so it can be installed like this. Different configurations depends on how much they need energy. And we have 23 million households in the Philippines, and only around 218,000 households have solar panels installed as their source of energy. So the point is, if you have a lot of storms passing through the Philippines, these renewable energy systems, such as solar PV panels, they need to be protected from these typhoons, and they have to be structurally resilient also as well. The problem is that the building codes are not really clear about where to put the panels in order for them to be protected from natural elements. So what we can do is that we can estimate the damage that the panels will have, or we can position them properly using a combined framework of structural resilience and energy assessment. So in the structural resilience, we're going to combine fluid dynamics, computation of fluid dynamics, and finite element analysis in this case. And then this will result in the fluid structure interaction. And this can predict how much damage will occur in the panels when a certain storm passes through the roof. At the same time, we wanted to check whether the panels that are installed in those roofs may be able to power through the household and its occupants using BES, or building energy simulation. So the data coming from the FSI, this will be performed independently, and then we can perform the BES also independently, and we can combine those results in order for us to say what is the proper panel configuration and the roofing that is which is optimum for the panels to survive a storm and at the same time power through the house. The reason why we wanted to put some panels in the house is that in the Philippines, when the storm passes through, there will be a blackout, and most of the blackouts were long, like 1 month or several weeks. So we wanted to have a power grid independent infrastructure placed on the roof of the houses so that they can continue on with their lives, and the quality of life will still be sustained even if they don't have any power from the grid. So this will be our aims and objectives. So structural resilience of the energy system and BES. So we're going to subject our building to two wind speeds, 41 and 61 meters per second, and 3 different wind angles. At the same time, on the BES, we're going to locate our building in the city of Tacloban and test different site orientations and measure the solar energy, the generation of the solar energy in the roof. So this is a graphical abstract we're going to do. So we're going to do FSI modeling. So we're going to, of course, we have one base building, which is have the PV system, the weather data, roof design, and this will be shared across BES and FSI modeling. So this will be our building, which is just a small building. So we're going to subject it to 2 wind speeds, 41 and 61. 41 meters per second is 147 kilometers per hour. And the higher wind speed is 61 meters per second is 220 kilometers per hour, which is a super typhoon category. So 3 different wind directions, wind flowing from this side, 45 and 90 degrees. So the panels will be mounted on the roof or made from SunPower E19 solar panels. And the building size is 25 square meters. The reason why we are going to put it up is that in rural communities, the houses are very small. And for low income economic housing, typically the floor area is just 20 to 25 square meters. So we wanted to target those low income communities and see whether they can be, if there's going to be rebuilding, we want to build some houses that are resilient to future disasters. So this is our base model 30. We're going to test also 26.5 roof pitch and a higher roof pitch of 37 degrees. So we wanted to see what will be the effect of increasing the roof pitch on the performance of the solar panel in terms of generation, at the same time in terms of structural resiliency. So in the BES setup, we're going to put this is city of Tacloban. All of the weather data, the solar energy data will be based on the city of Tacloban. And this will be the building, and then we can change the orientation of the building and determine which is the proper site orientation. So this will be 0, 45, 90, 180, 270. So for internal loading, we're going to put 3 persons inside. Is 2 windows on the opposite side, 1 stand fan for space cooling, 2 CFL lamps, and 1 television for recreational use. So this will be the results for the CFD. So we will test, this will be the wind 41, 61 meters per second, and this will be the different wind directions. And these are the surface coefficients of the different rooftops, buildings as well. So as you can see, the surface pressure coefficient changes. It depends on the direction of the wind. And that will be transferred to the finite element analysis to complete our FSI. So what will be the result of that? This will be the result, the equivalent stresses. So we wanted to see whether our building or our panels will be able to withstand the wind gusts. So if the stress exceeds the design stress of the tempered glass, which is installed in the panels, then our panels will fail. So as you can see, in the if you put our panels behind, the wind is blowing through this direction, this one, most likely our panels will fail. The same is true in the 90-degree wind direction. And for the zero, the panels in the windward side will fail. So if it's closer to the edge, it will fail. So what would be the implication of that? So as you can see, the panels will fail along the edges because this would be the highest equivalent stress. So it would be pulled up in that direction. So as the worst case scenario for the angle will be around 45 degrees. Okay. So in this scenario, most of the panels will fail if the wind is blowing at 45 in an oblique angle. So in this scenario, at 41 meters per second, all panels on the leeward side will fail. But if you put the panels on this area, they will not fail. But however, if you increase the wind speed to 61 meters per second, most of the panels in any location at 26.5 and 30 will fail. So this will be the only panels that will survive if you install them in these areas. For 37, most of the panels in the windward side will still be able to function. For BES, we tested the energy generation at different site orientations. And as you can see, at different site orientations, if you situate your building 180 degrees, you will get the highest potential, energy potential. And as you can see, the months of April, May, and June are the highest because these are the summer months in the Philippines. But in any month, if you the equipment load, the solar panels will be able to sustain the equipment, the occupancy loads, the energy demand of the building at any site, at any month. In terms of altering the roof pitch, the lowest roof pitch of 26.5 will have the highest generation at any site orientation. The lowest will be the highest, which is 37. If you're going to combine the results with the FSI, meaning in terms of how many panels will fail, as you can see, even at a lower speed, at the worst case, if the wind is blowing at the worst case scenario, it will be able to sustain even the wind, the energy loads of the building. However, if you increase the wind speed to 61, 220 kilometers per hour, the panels will not be able to sustain the building energy loads now, except for 37 degrees, which can still sustain it. So conclusion is that we developed a coupled FSI and BS model to study the performance of low-rise residential buildings with roof-mounted solar panels under typhoon wind conditions. In the previous system, the worst-case scenario 45 degree can power the household in the aftermath of the typhoon at the wind speed of 147 kilometers per hour. If it is increased to 200 or 220 kilometers per hour, most of the panels will be destroyed, and most likely the system will not be able to power the building and its occupants. And based on where to put the panels, it's recommended that if you install it in the windward side of the roof, if you know the direction of the wind in this case. So in this case, it's a case study. We can say that we can predict where to put the building, where to situate the building, if we know the wind direction of the typhoon. And we can, in future disasters, we can future-proof our homes so that we able to withstand the wind of the typhoon, and at the same time be able to sustain the household even in the event of a power failure. So thank you. And if you want to have questions, you can email me, or yeah, and both email addresses. And thank you for listening.